An accurate analog square root computing circuit with temperature compensation is explained in this 216 circuit design and analysis video. We want to see how it works and then do a quick analysis. The circuit has input voltage that is assumed to be non-negative, so between 0 and 10 volt, and then the output current is measured in microamp by this current meter. So the relationship between that and input voltage is just by multiplying input voltage by 1000 and then take a square root. A very simple relationship. Okay, so the circuit has one operational amplifier that is assumed to be able to operate in single supply mode and with zero or very low input drift. As you can see that the top supply is connected to ground, that's the highest voltage in this circuit, and the lowest supply is connected to negative 15.7 volt in this example as a regulated voltage, which is also referred here. So we need it to be stable and regulated. Okay, so the connection that we have is we have 4 bipolar junction transistors that are preferred to be all matched in a quad package. If not possible, then TA1 or transistor A1 and transistor A2 need to be matched together, and then TB1 and TB2 as another pair or second pair that need to be matched with each other. The two diodes here are mainly for temperature compensation. They should experience the same temperature as the junction of these transistors. Okay, with that said, the main 3 resistors are R, 1.5R, and 3R. These are required to be relatively accurate resistors with low tolerance, like 1% or better. Contrary to that, the 2K and 1.2K resistors, they just need to be as good as 5% or better. Okay, with that said, let's do an analysis for this circuit. So first thing, we're going to use the, one thing to mention, I'll do the analysis later, but then here there is a negative feedback in this circuit, which enforces the virtual short for the input voltage of the input terminals of the op-amp. Basically here we have 0 volt, and via negative feedback, it's also guaranteed we have a 0 volt here in steady state. So with that said, I'm going to just write down a KVL for the route from this ground terminal and this ground point. So I'm going to just write a KVL across these 4 base emitter voltages of the 4 NPN transistors. What I'm going to use is the famous Shockley diode equation that relates the voltage of base emitter with the current of the collector. So we have voltage of base emitter of a given transistor equal to eta Vt, and then we have natural log the current of collector divided by the saturation current. Note that the saturation current is well known to be on the order of cubic relationship with the temperature in Kelvin, very sensitive to temperature, while the thermal voltage Vt is well known to be kT over Q, in which K is a Boltzmann constant and Q is the electron charge, and T is just temperature in Kelvin. As long as the IC for a given diode connected transistor, or basically a transistor, as long as IC is constant, it can be shown that the voltage of base emitter changes with temperature on the order of roughly negative 2.1 on average millivolt per degree Kelvin, as long as the current is constant, roughly. Okay, so with that said, let's write the KVL. So I'm going to write the KVL in this circuit, and here is my KVL. So using Kirchhoff voltage law, I can say voltage of the base emitter for transistor TA1. So let me just write it here. Voltage of base emitter for transistor TA1, which is this voltage, plus the voltage of base emitter for transistor TA2, okay, TB1, sorry. TB1 should be equal to, from again, 0 volt, like the 0 volt here. So we have a VBE of TA2 drop, so voltage of base emitter of TA2, and then plus the base emitter of TB2, and then we get to common emitter for these pair of transistors. So voltage of base emitter for transistor TB2. Okay, now I am going to use the Shockley diode equation or diode law, which basically says Okay, I can replace these guys with eta VT and then natural log of ICA1. So let's refer to it as IA1, and then we have ISA, which is the saturation current for TA1 and TA2. Because they are matched, they should have the same saturation current roughly. So plus the same thing for VE TB1 for this transistor. So we can say that's eta VT natural log I base 1 divide by ISB, because these two transistors are at least matched. Again, if we can't have the four matched transistors, equal to the same thing that I'm going to copy paste, and then I am going to just make a little change to just rewrite them. So here is my equation, copy paste it, and so that we can see what's going on. Let me just double check that. I am. Yes, okay. So here I'm going to make the change that IA1 becomes basically IA2 and IB1 becomes IB2. Okay, so what is the nice thing about this whole scheme here? The nice thing is the IA1, the current of this transistor. So let me just make the correction. The current of this transistor is referred to as I reference for now. So I'm going to show you that's a reference current that depends on this regulated V reference voltage. So I'm going to refer to this as I ref. Okay, IB1 is the current of this transistor, which is of course defined by the input current I in, which is controlled by Vn and this accurate resistor, because on the other side we have 0 volt enforced by virtual short of the op amp. So this one is I in. Okay, and then what about the IE2? IA2 is the output current, as you can see here, from collector to emitter roughly. So I out. Okay, so what about IB2? IB2, it's a diode connected bipolar transistor, so therefore I out is again repeated as well there. So we have I out in IB2 as well. Okay, so with that said, one thing I can cancel out in this equation is of course roughly, because these transistors are seeing the same temperature roughly. I can just make the assumption that these eta VT can cancel out from all sides, and therefore what we get is, I'm going to write it here. So what we get is, I can say ln natural log of I ref, so here, divide by ISA, plus natural log of I in divide by ISB equal to ln I out ISA, and then plus ln I out ISB. Okay, the best thing to do is I'm gonna move this ln to this side, and I'm gonna basically move all of them to one side. So or doesn't matter, I can move it to any side I want, but then let's just move let's just do it this way. Okay, then move everything on one side. So if I move everything to one side, these two become negative, and then we have equal to 0. Okay, what's the benefit of doing it that way? We can combine this log with this one here, and as a result of that, it becomes natural log I ref divide by ISA, and then we have I out divide by ISA. So the other one also, these two guys, given the negative sign we have here, becomes natural log, and then we have I in divide by ISB, and then we have I out divide by ISB equal to 0. Okay, so what's the benefit of having it this way? The benefit is obviously ISA cancels out with ISA, ISB cancels out with ISB. Therefore, we get rid of the parameter, or let's say the variable that is very much depending on temperature in a cubic fashion, which is the one we really don't like. So with that said, Therefore, our equation simply becomes ln of Iref divided by I out. And if I move the other component, which is this one, to the other side, it gets a negative sign, which will result in just exchanging the numerator and denominator. So it becomes I out divided by I in. Okay, because natural log is a one-to-one function, at least for the range of values that we have in mind. Therefore, we can just get rid of the natural log. As a result, the only solution that we can have out of this one is Iref divided by I out equal to I out divided by I in. And we get the very important relationship that I squared is equal to I ref times I in. Okay, we almost got what we wanted. So I can just write it this way now. Okay, so I can just write it this way. I out is the square root of I ref times I in. Almost there. Okay, so you can see that in our relationship in the target equation, we are looking for I out in microamp. So on one side, which we are almost getting it. So there you go. So I'm gonna rewrite the equation now by substituting for I ref and I in. That's the part I need extra explanation here. So let me just make sure that I have a color. Okay, therefore, here is the thing. I ref is, let's start with I in. That's easier to do. I in is the current of input that is basically controlled by Vn on one side of the 150K resistor and the 0 on the other side. So I can just simply say the I in that is flowing through the 150K resistor is simply equal to, so I'm going to write it, I in is simply equal to V in minus 0 divided by R, 1.5 R. So in this example, it's V in divided by 150K. Okay, that's I in. Now, what about the Iref? Well, Iref is the current of this diode-connected NPN transistor. As you can see here, the input current I in, as I indicated, is going to be a current that is controlled by this equation. And because V in is a value between 10 and 0, and given in denominator we have 150K, so at max V in can be 10 volt. So therefore we can write, I'm going to write it here. I'm going to just write it here. I in max is equal to 10 divided by 150 kilo ohm, which means is less than or equal 70 microamp. So it's less than 70 microamp. If this current, the reference current, is at most 70 microamp, then given that the current gain or beta or HFE of this transistor is at least 100, then the base current, I base, is 100 times less than this 70 microamp, so on the order of less than 1 microamp. Okay, but we can see that the current of this diode-connected transistor is also on the order of, as we can see, is controlled mainly by this resistor, and on one side we have negative 15.7. On the other side we have roughly 0.7 volt in nominal operation. So the nominal voltage of emitter is negative 0.7. So the voltage drop across this R is about 15 volt in nominal operation. So therefore the current of Iref is roughly just 15 divided by 100K. So I'm going to write it here. Iref is equal to, with a very good approximation, is equal to, we have on one side minus 0.7, the voltage of base emitter, and then negative 15.7, the regulated voltage we have, divided by the R, which is 100 kilo. So we end up with 15 volt divided by 100 kilo. That's the IREF. Okay, so in conclusion, what I'm trying to say is this voltage obviously is clearly is 150 microamp. So we are dealing with 150 microamp for IREF, but for IREF, while I base is less than 1 microamp. So all I'm saying is that I base is completely negligible compared to the IREF that flows mainly this way. The other voltage is going to be minimal as well because there is from ground. There are there are 2 base emitter and 2 diode, all of them 0.7 volts. So roughly the voltage here is negative 4 times 0.7, which is about typically on the order of negative 2.8 volt. Okay, so the voltage drop across this 3R, on one side we have negative 2.8 or 4 VBE. On the other side we have just negative 0.7. So the voltage drop across this resistor here is going to be, sorry, the other way, is going to be 3 times 0.7, which is 2.1 volt. So given that it's 300 kilo ohm, you're talking about a minimal voltage, a minimal current that is again at least 20 times less than the IREF. So all I'm trying to say is the current of IREF for the diode connected transistor, BJT transistor, is dominantly controlled by the 100 kilo ohm and by the regulated negative 15.7 supply voltage, and the rest of currents are negligible. Okay, so I'm going to substitute in our equation, I'm going to substitute the values I found for the I out and for I in and also for IREF. So therefore the value I'm going to get is equal to I out equal to square root IREF is 15 volt divided by 100 kilo ohm. So basically divide by 10 to the power 5 ohm. And then I in is V in divided by 150 kilo ohm. So therefore what we're gonna get out of this equation is simply we're gonna get Vn divided by 15 by 15 cancels out, and then what leaves is 10k, which is 10 to the power 4, then times 10 to the power 5, it's going to give us 10 to the power 9. So if I simplify this, what I'm going to get is going to be, okay, I'm going to write it in this format. So 10 to the power minus 9 Vn, and then I'm going to write it in the format of 10 to the power minus 12, 10 to the power minus 3, 10 to the power plus 3 Vn. And then this 10 to the power minus 12 is extracted outside, becomes 10 to the power 6, negative 6, and then we have 10 to the power 3 Vn. This is the one that converts to microamp, and this is the equation that we had at the input of the circuit. So basically, we proved the relationship that was given for the current as a function of voltage. Now, why this, with that proven, for further analysis, why we have negative feedback? We have negative feedback because if for whatever reason suddenly the voltage at negative input terminal of op amp goes high because of, let's say, reduction in current, then the output of op amp is pushed because the voltage of negative terminal becomes more than, say, 0 volt at the positive terminal. Then output is pushed to maximum lowest voltage, which is roughly negative 15 in this case, or negative 15.7. And then because of that, when it tries to push down, it means as a result, the current here So the direction of current, as you can see, is via this route. So the direction of current, overall speaking, is this way. So there is a feed like this, and this feed all goes this way. There is a feed like this, and there's a feed like this. So all of them going this route. Okay, so when the output of the op amp suddenly hugely drops, it will pull down. It will pull down and increase the current that is flowing through the diodes, and therefore the current that flows through the transistor increase, which means it will result in the current in also increase because it's increasing more current, and that means more drop across the 1.5 resistor, and then that means the reduction in the voltage. So hence the circuit is behaving in a sense of counteracting what was the source of the issue. You can also do the same analysis by considering that if suddenly the voltage here drops below zero because of increasing current, then the output of op amp will jump to zero, which is the maximum output because it's controlled by the supply, positive supply, which in this case is connected to ground. So at zero, then it cuts the or it heavily reduces the current. When it heavily reduces the current, this current also going to reduce the current through the transistors, which means therefore the current drops, and hence we have, and therefore the current drops, and therefore we have less current across the 150K, which means increase of 0 volts, so counteracting the source of the problem. Okay, so I hope this shows how the negative feedback in this circuit works. Now, for the temperature compensation, the interesting observation is because the IREF is constant, so the current through this TA1 is constant, and because the current through the TB1 is also constant, controlled by Vin and 1.5R, so IC is counted as constant for these TB1 and TA1, and therefore the voltage of these transistors will drop about roughly 2.1 millivolt per degree Kelvin or degree C as the temperature is increasing. Okay, so with that said, we can observe that, as I said, the voltage across this one is 3 VBE with the direction that is shown, like this, with the polarity. And that is 3 VBE across 3R, which is drawing a current this way. Now, the voltage across the base emitter of TA1 is dropping, which means the voltage across R is increasing by 1 VBE. So all I'm trying to say is, on one side, we have this voltage increasing equal to VBE over 100K, resulting in current. On the other side, we have the same amount of current decreasing. So effectively, the sum of these two currents that I'm going to show with different colors. So here is one color. Here in basically green, which means the current is increasing because the VBE of TA1 is decreasing with temperature, and hence the voltage drop across 100K is increasing by delta VBE, or 2.1 millivolt per degree Kelvin, while this one is actually dropping by 3 times 2.1 volt across this resistor. So the increase and decrease of the current counteract each other. Therefore, the current through the reference TA1 is not affected by temperature. That's how the temperature compensation is working in this circuit. Okay, so I hope this sort of analysis of how this circuit works, why we get this equation, why we have negative feedback for the op amp properly operating, and therefore virtual short is enforced, and why the temperature compensation is working by the connection of a cascade of 4 basically base emitter or diodic connection that helps with the way that we have constructed the reference voltage and reference current in this circuit. I hope this is helpful. Thanks for watching.